You know, I want to be teacher's pet. I don't even care if she likes me, but I want to be treated fair, you know. If I can submit the test, let's find out who did and why.
Where did we leave off? Y'all remember on what symbol? I think it was capacitor, maybe?
Really quick question.
Yes.
You have a power consuming device in the circuit, like a load. Is there always a voltage drop across that load?
I guess I would say yes. Depends on what you mean by voltage drop.
I guess, any load is going to have like a resistance to it.
That's right.
You always be able to put a voltage drop if you cross the you probe voltage reading.
That's right. It depends on if it was in series or parallel, but there'll be some kind of voltage drop. So Gerard, Mr. Collins, Mr. Crawford, Gerard Dees, Lewis, Falconer, John, Kenny Jones, Mr. King, William King, Mr. Macy. Let me get this right. The Keys. Yes. Mr. Miller. Perry. Sam Ray. He's not coming. Okay. Mr. Wood. Everybody didn't call? No. You're on the night? Okay. Alright. Get started here. So, we were going over symbols, and we had stopped on capacitor. So the next symbol here is what we call, it's a switch. Remember we covered a manual switch, right? Like that, like a light switch. You can label it. Door switch, light switch. And then we said, well, we could put a flag on it that would tell me what opens and closes it, like a pressure switch or something. But here we have a different kind of switch. Now that is called a normally open, because the electrons can't flow across it. And this is called a normally closed, because electricity can cross it. We don't have a flag here, but either one of these are what we call automatic switches. Okay, so automatic switches are controlled usually by a coil. Usually by a magnetic coil. And the most common would be a contactor or a relay. If you look here, I got a coil here. Right? We said that's step one in making a magnet. Take it. You wrap it around. Here. Wrap it around to increase the strength. Wrap it around a iron core. Iron core. I think I got one somewhere here. And this has to be laminated. The good thing with lamination is when I cut the magnet off, it's no longer a magnet. Because a lot of times just regular unlaminated will become magnetized. We used to do that. You wrap it around, say, just a solid steel flat tip screwdriver. And once you cut the magnet off, it would still pick up paper clips because it had become magnetized. And so by laminating, in other words, cutting in slices and turning it, cutting it, turning it, you get a core and a coil. That's going to create a magnetic pole. Somewhere in here. There's another one. That magnetic pole is going to well, not on the push button. Push button is a manual. But anyway, I don't have that here. That's going to pull the armature down, the plug. On the back of this, if we took this apart, you'd see there's a steel plate. And when this becomes magnetized, pulls it to it. That overcomes the spring. Here I have it inside of a relay. A relay, same thing. I don't know if y'all can see this, but there's a coil here. When it does, it pulls the spring here, and it makes out here this close. And lets power flow through, right? So those are automatic switches. And sometimes normal, we use the term normal, right? Normal means de-energized. In other words, the coil is not energized. Once I put 24 volts on it, it's energized. It's going to go to the opposite. If it was normally open, now it's closed. If it was normally closed, it's now
Open.
That's right. Okay? What we got next? If I jump some on your sheet, let me know. So these are my coils here, y'all. Yeah, John. So what we got here, a coil, is simply electrical wire, a conductor wrapped around many times. And you got 3 there and you got 5 there. There is no set limit, right? So that's what we call a coil. Some people draw them a little different. They may do them like this. Doesn't matter, right? As long as you can understand, you go, hey, that's a coil. So this coil may control this or both of them. The way to make this control it is to label it. In other words, if I label this X, coil X controls any normally open or any normally closed switches. Label that. So if this one was labeled Y and this one was labeled X, this one would only control this one, not that, right? And we usually give them a name that's a little more common, like CC for compressor contactor, that kind of thing. BMR for blower motor relay, or FR, fan relay. Okay, but that's what we mean. When this is labeled, then you look to see, hey, what is controlled. Now this especially, can also be controlled by a sequencer. And we'll get to that later on at the very end of this. Okay? Now, some, like in your textbook, and some of the older stuff, they use this to show a coil. Kind of like a little heartbeat. We prefer to use this and call it a solenoid. A solenoid. You go? A solenoid is the same thing as a coil, really. Take a bunch of wire, wrap it around iron core, and it creates a magnetic field. And you're going to say, well, why are you using a different name? Typically in our industry, what we do is we use a solenoid term and symbol when I open and shut a passageway for something that's not electrical. When a coil closes that contact, what goes through it? Electricity. Or if it opens that contact, stops electricity. But a solenoid, y'all know what this is? That's a gas valve. This regulates gas to, it's a combination, but what we call a gas valve. It regulates gas to the furnace. In other words, it opens, it shuts. When I want heat on, opens up. I don't want gas flowing all the time. Shuts. So there is a solenoid. There's actually two in here. Can y'all see this in here? Redundant. That way if one gets stuck with some trash in it, we don't keep flowing gas. So we have two redundant. They both have to open to get it to work. And so here we're letting gas flow through. So if I was drawing this symbol, I might put GV in front of that symbol and say, hey, that's my gas valve. You probably have one at home if you have a refrigerator with an automatic ice maker. It's a water valve. That's a solenoid. It opens up and lets water into the ice maker to fill the ice tray. And then it goes through it, freezes it, hardens it, cuts it, drops it, and says, hey, if the arm is up or down, refill it. Okay? We have a four-way valve on a heat pump. There's different ones, okay? But they are solenoids. Y'all see the difference between letting something physical through as opposed to letting electricity through. Okay? And I would never count that wrong. You're going to see that sometimes. You're going to go like, well, Clay, they use the solenoid. And you go, well, so be it. But as you work with more ACR and then the HVACR field, you're going to see we use that more. If you see something that's just electrical, maybe it's made by electricians, you might use that symbol interchangeably. Okay? What we got next? Bimetal switch. Okay, now let's talk about this for a second. Bimetal. Okay, they're trying to confuse you. I have two metals. We call them dissimilar. Another trick word. That means it's not the same. It's not copper and copper. It's not silver and silver. Tin and tin. They're different, dissimilar metals. So they take these two metals and they bond them together and fuse them. Well, if you know anything about metal, if you've ever played on actually, if you played with a basketball, you go out on a cold day and your basketball's flat or flat turf. But on a good hot summer day, sit in the sun, it's full of air because the gas will expand. Same way with metal. You heat it, it's going to expand. You cool it, it contracts. And everything does that at its own rate. And so when I have two pieces of metal that are joined together, they can't get loose, the one with the greater contraction rate will warp it, right? They're both trying to contract, they're both trying to expand, but the one that expands more is going to warp over it. And when they contract, same way, it'll warp down. That's what we're talking about. We're working with warpage. And so they take these things, we just draw it like that. And so they are sensitive to heat. I've got some in here. So this is a bimetal switch. Does anybody have a lighter? About to smoke? Well, if you did, we could put it under here, and that metal will warp. And when it warps open, the electricity can't pass through it. This one says L175-40F. That means at around 175, it's going to open. When it cools down 40 degrees below that, approximately it's going to close. Okay. Here's one that has, when this thing overheats, it has a reset button, manual. So that one goes back to based on temperature. This one, once it pops open, the only way to close it is to reset that switch, and that was bad. I don't think it will reset at all.
So what is stopping from going to heat?
What a what?
What is the light of the switch stopping?
Electricity. Yeah. Okay, so I got electricity going to my gas valve. And let's say for some reason the blower motor, the fan doesn't run. So it gets hotter and hotter and hotter, and the thermostat, there's no air coming out in the room, so it still wants it. And instead of the furnace catching on fire, this thing will warp and cut the power to my gas valve, maybe, and be a safety. Same way with strip heat. It's very similar, y'all. Remember the first day we talked about a thermal overload. Remember? Except for this is a little simpler. Transformer. Transformer, right? Alright, so here I have a transformer, and most of you probably went over this in here's that laminated steel if you want to look at it. Y'all probably went over this in basic electricity, running out of board. So let's talk about how a transformer is made. So I take an iron core, alright, laminated steel. Why would I use laminated steel? Permanent magnet, that's right. So I take a core, winding, right? So I've created a magnet. Pretty simple. And by the way, whenever we create a magnet or use a magnet, we call that induction. In other words, that load is going to be called an inductive load because it's using magnetism. So this thing creates a flux field. I'm sure Brian talked about it. Basic. So it's creating a magnetic field of plus and minus or north and south, however you want to look at that. Well, electron theory law, the physics of it tell us that if I put a conductor, an iron core, in the field of a flux field, that's a magnetic field, if I do that, I can cause electrons to flow, which means electricity. So I take that iron core, that conductor, and I create electron flow. There is no connection. Let's say this is 240 volts AC. There is no wire connection. I'm like, well, hey, I'm just going to put a little of it together. No, there is no wire. We create a magnet, and that magnetic field crashes through this conductor, which causes it to create electron flow. And it does it on a ratio. So if the ratio is from start to finish down, then it steps down. If it steps up, if the ratio goes up, let's say I had 1,000 racks here. And And on this side, 100 wraps of the same diameter of wire. That's a ratio of 10 to 1, right? 1,000 to 100. And so I will step it down by 10 to 1. So putting 240 in, get 24 volts, and that'd be my control voltage out. Okay? What if I stepped it up from 1,000 to 10,000? Then I would be stepping it up 10 times, right? That would give me 2,400. That's how transformers are made. But don't get me wrong. This is not an energy efficient production of electricity. You're like, well, they ought to make transformers on. They get hot. You put your hand on one in your air handler, and go, man, that thing's warm. Because it's not energy efficient, but it does, it's laws of physics, it does work. So we do have a step down by adjusting this ratio. I can still step down to what I want. So I carry this transformer on my truck. It steps down 240 to 24, right? And I said, well, you know what? What if I put a tap here? Instead of using this one and this one, what if I used this one and this one? And this one was only 500. 500 to 100. What's that ratio? 5 to 1, right? And so if I inserted 120 volts here and it stepped down 5 to 1, I still get 24. See what I'm saying? So I can make it a multi-tap transformer. It all works off a step down. And so our symbol here, y'all, if you can recognize it, is 2 coils. Isn't that what we have? We have a coil here and a coil here. And divided by, this is supposed to be conductors, right? Remember, the flux field passes through a conductor. That's my transformer symbol. Okay. Mr. A fuse, I think I told you a fuse and a fuse plug, the most commonly missed one on my first test. There's a fuse for you. 400 amps. 400 amps. So what is a fuse? A what? A break?
So, safety switch. One time use safety switch.
Simplest type of safety switch there is. When the heat becomes too much, the middle of that fuse, what we call a filament, will melt. And it's usually done by amps, not real heat. But if you know, there's real heat in electrical amps. By the way, y'all, I showed y'all a contactor, and I said the coil will pull it back. Y'all see the metal right here? That's what I mean. There's a metal plate at the back of this, and that magnet pulls it down. All right, so where are we at? A fuse. The simplest type of safety device works off of heat. Works off of heat. Electrical heat. What else we got? Pressure switches. So, got a different kind of flag, right? The one we looked at the other day was temperature, right? So this flag means pressure. And we can have a low pressure switch, a high pressure switch, right? What is this one? What kind of switch is this kind of pressure switch?
Open on high pressure.
That's right. When the pressure builds, boom, opens up, protects my compressor, hopefully. So, what kind of pressure switch is that? A low, right? Pressure drops, what happens? Opens up, protect my equipment. Okay.
How does the pressure switch look?
What now?
How does the pressure switch look?
How does it look? Oh, I'm sorry. All right, so here, this is a high pressure switch. Sorry, I don't have a low pressure switch, but it's going to look just like it. Pretty much just like it. And that would have, what's been cut out of that green is 2 wires. So normally the electricity flow right through it, but when the pressure switch trips, it's going to open up and not let the power through it, right? When this opens up, y'all, the electricity can't flow anymore, right? All right, the last one, it's not in yours, draw it in there. It's called a sequencer. Kind of looks like a castle wall, or some people say a pumpkin's teeth, right? Now a sequencer is somewhat of a unique item. Some people call them fan sequencers. Most people call them strip heat sequencers. Do I have anything above that? This is a sequencer. I'm going to let you go around. This is a 2-level sequencer. When you look at this, the first thing that'll jump out at you is these at the bottom, that I'm holding upside down now, are brass. That's our 24-volt section. Now, when we supply 24 volts to it, it doesn't create a magnet, it creates a heater. And so it creates heat. And if you look at this one, these are labeled 1, 3, 4, 5. 2 different levels, right? Inside of here, y'all, is bimetal. What happens to bimetal? It warps. And so as this heater heats up, it'll start making, from the top usually. The first 2 on the top will close, then the next one, and you might even have a 3 level. So this is a little different than a coil because it works off of heat. Now because of that, you would have the sequencer. When it's energized, it's going to close normally open contact. Now some people draw a sequencer. Do you remember the resistor heater symbol? Just back and forth. Y'all remember that? The heater symbol? If you want to use that, that's fine. If you want to use the sequencer symbol, you can use that. you still need to label it S for sequencer. You've got two sequencers, S1, S2. This is actually, this symbol right here, y'all, actually means time delay. Now, why would a sequencer use time delay? Okay, I'm going to tell y'all how. Because this can draw more power than anything in your house. This is 5 kW, about 18, 19 amps. Depending on your size of your house, you may have 4 of these. 20 kW, 80 amps. Now, some of these big fancy houses have a 200 amp circuit. That's almost half of theirs. Some of these other houses have 100, 80%. So, we in the industry and Alabama Power and them do not like it when you cut all the strip heat on at the same time. What do we want to do? We want to sequence them on. Does that make sense? And so that sequencer brings on the first strip. And it continues to heat up. Then the second set closes, 10, 15 seconds, 30 seconds. Then it brings on the second strip. If you got a third strip, then it brings them on. If you got another set of sequencers, they sequence on and they sequence off. The last one to make will be the first one to break. It'll cool off quickest when the power. And so when this thing cuts off, it doesn't just the 24 volts. It doesn't just cut off quick. It's got to cool down. All right. We don't want it like a coil on a relay or contact. We don't want to bring that strip on right on all of them together. On some really cheap manufactured equipment, sometimes in the heater kit, they give you a contactor. And so it doesn't sequence on at all. And that's considered pretty cheap. Not to mention contactors, when you have a voltage problem on the 24 volts and the coil starts losing draw power, a lot of times it'll chatter. And that's a lot of noise in the ductwork. So sequencing and using a sequencer is the best choice, okay? All right, let's talk about the first test will also take into account some terms. I want to run over these. We'll probably have that test Wednesday. So, a load, an electrical device that consumes electricity to use for work. This is on Blackboard, right? It's listed as PowerPoint. I think either PowerPoint 1 or just PowerPoint. 2, a motor, an electrical device that consumes electrical energy to rotate a device in an electrical system. How about that, Luke? Solenoid, a device that creates a magnetic field when energizes and causes some action to an electrical component, right? Our gas valve opens up, right? Our reversing valve slides. Our water valve opens up, That's what it's causing an electrical component to do. What else we got? Heater, a device that uses electrical energy and converts it to heat. Contactor and a relay, devices that open and close a set and or sets multiple of electrical contacts by the action of a coil. Doesn't have to be a solenoid coil. Of a coil. Normal simply refers to the position of those automatic switches when they're de-energized. A switch, a device that opens and closes to control some load in an electrical circuit, right? Like that light switch over there. Fuse. The simplest type of overload device, we said. Safety device. Transformer. A device that decreases or increases the incoming voltage to a desired voltage through induction, which means magnetism, right? Alright, and we had a little bit afterwards here, let's see. Probably Wednesday. Alright, so this is all on here with pictures of that stuff we went over, I think. Alright. Alright, so let's talk about diagrams. Let me get two people to help me out here in the lab real quick for just a second. We don't have her back.
It's more than he just did, you know. What was he right here? Okay, you leave right here, it's the ones that we just turn in on the right, on the second and the third.
Easy now, don't hurt yourself.
Right about there.
It's important. Let's go over this done.
Alright, so what we have over here in the industry is called an air conditioning condenser. And it is, not to be confused, it is not a heat pump. It will be used in tandem inside with an evaporator. And in the industry, we call it a condensing unit. Right? Maybe I'll put it up here in the middle. Now, y'all have all had basic refrigeration too, probably, right? Not just basic electricity. Can you name the four components of a refrigeration system?
Condenser, evaporator.
Compressor, not a four major part.
Evaporator, condenser,
Meter device,
metering device, and compressor.
compressor, meter device, what are the other two?
Evaporator, condenser.
Evaporator, condenser. So evaporator and the meter device are usually inside. Outside, I got a compressor. I don't know if y'all see back in here, but there's a little black scroll compressor. And this right here, wrapping around it, is my condenser. But they call this a condensing unit. If you go, hey, I need a compressor and a condenser, they're going, what? You want a condenser unit, an AC condenser unit. If you wanted a heat pump, you Say I want a heat pump condensing unit. You know, what size? All right. So first thing we want to learn is how to wire up an AC condensing unit. So this sits outside. Usually, there's a few chances of not. And this is not to be confused with the package unit, y'all. Package unit has all 4 components in it and sits outside. This only has 2 of the refrigeration systems. So the first thing we need to recognize in doing this is what's in here. You know, as electrically speaking. Because there's only 3 things that we have to have. Path, load, and source. And obviously we're probably going to have some switches. So, the first thing I see is a compressor. Of those 4 things, how would you classify a compressor electrically? Bingo. It's a load because it's got a magnet inside that creates rotation. So it's an inductive load. Inductive load. The next thing I see is a condenser fan motor. I don't know if y'all can see it up there, but the blades, can y'all see the blades here? Now on a heat pump, the evaporator and the condenser change. In other words, we send hot gas inside, that would make it a condenser. We send it outside, make it a condenser. So when we change modes, the evaporator and condenser change. And so on a heat pump, we often just say outdoor fan motor. But since this is an air conditioner, it's a condenser fan motor. How would you classify a condenser fan motor electrically? Tap load or source? Or a switch? What is it? Load. What kind of load? 3 types of loads. Capacitive, resistive, and inductive, right? And a motor works off a magnet, which means inductive. What is this? Contactor. Contactor is 2 different things. Break it down. First of all, it's a set 2 normally open contacts, right? So it's path. The contacts normally open contacts are path. Right? They're open, path is open like a switch. When they close, the path is closed. And the second set, like one of those coils sitting in front of Mr. Crawford, right? It's a coil, right? It closes those contacts. So it's both path and the coil is an inductive load, right? Because it uses magnetism.
What kind of load?
Inductive. Induction means magnetism. Induction means magnetism. And then finally, I'm missing one. I have one up here at the bottom. I got what? 2 run capacitors. Compressor run cap and condenser fan run cap. Alright, these are loads, but they are capacitive loads. And everything else, what would y'all call this? All this stuff. What is this known as? Wire. And what is it? Pad. That's right. 6. And at the bottom is wire. And it's known as pad. So we've clarified everything we got. So I want to look at this. I want to clarify this in two types of diagrams. The first is going to be a picture, and then a schematic. All right. This is how it works. A picture diagram shows me how the equipment is wired together, and it's labeled correctly. So I need to put all 6 of those on here. So I'm going to draw it like this. Compressor. Condensing fan motor. Contact. Run cap. Run cap. Fan run cap. Compressor. What else was it? Okay, so I gotta add the wire. Now, the better the wire diagram, the more detail. Okay? So, what did we say power coming into a contactor is called? What kind of voltage? Line voltage. And we will call it L1 and L2. Now, across from that, what do we call the power? Instead of line voltage, it's load voltage. And we're going to use T's. T1 and T2. My compressor,
What is T1 stand for?
T stand for load side. L stand for line side. We can't use L for both. They both start with the word L, so we just chose T's for the compressor. Has 3 electrical terminals on it. 3. And we name those 3 R, S, and C for run, start, and common. Condenser fan motor has 3 wires on it. And we label those common, start, and run on. Capacitors just have 2 electrical connections and they're not labeled. So I got all my labeling done. Now I got to put my wire. So let's see. all my wire here. There's the three, my fan motor, right? Put these over out here. Did I get an assistant up here? Give me a little assistant. Don't know if we have enough wires, but we're gonna try to. One last thing. That's a pressure switch and a pressure switch. We're going to pretend we don't have a pressure switch yet because that just kind of complicates it, okay? Okay. So, ready to go. One other thing, my contactor. What makes this contactor want to close?
Electricity.
Yeah, electricity on the coil. And so, I also have a coil. Alright, so I got 3 wires from the fan motor, 3 wires from the compressor. Let's start off with step 1. Yeah, we say we have 240 coming in, 24 to the side, and 240 coming out. Alright. So we're going to say this top side is the line voltage coming in from the disconnect. And this bottom side is the 240 going to the load. Now on each motor, he's got 3 wires here. He's got 3 wires here. I'm just going to tell y'all that the black wires on both of them, you pull that out. Thank you. Sorry. Those are common. So you want to go from right here, T1, the common, to common. So you have one side of the other. You choose it here. Same side, right? You're not going to the other side, are you? All right, we got it now. We said we want to be as accurate as possible with the wiring diagram. So what color are these wires? That's right, they're black. Step 2. Or it's really step 3. We'll go from a 4-step to a 5-step level. Anyway, we want to go from the runs of the motors to the other leg, T2. Okay, so he's got 2 wires coming up here. He's going to use yellow from the fan motor, and probably yellow from the compressor to the other side. All right, so from T2, I'm going to go to run, to run. And what color were those? Yellow. All right. Step 3. I want to go from T2 into my capacitors. So I need to find a wire. Do we have any on the floor? Oh, okay, we got some right here. So go from here to here. Okay, now that one's a longer one. Let's go there on that one. Either side. Then from here to one of those. Okay. So from T2 could have gone into either one. He could have too. And from T2 to that capacitor. Well, it disappeared on me. Alright, what was that? 3? 4 want to come out of both of the capacitors and go to start. So what color is start here? Brown. What color is start here? Blue. So that one's going to go to that other side of the capacitor. Does it have an end on it? Okay, good. That brown will go up there. We said that was brown. We said that was blue. The opposite side, that's right. It's got to go through it. All right, now the last thing. Back off. Just no, I mean that way. I got some wires here that say 24 volts from my T-stat. In other words, the T-stat, somebody went by, put it in cooling and said, I need air conditioning. So one of them is 24 hot, one of them is 24 common, and they go to the sides of the coil. Go ahead. Contactor, go to the sides. Volts, AC.
What you said those wires is?
24 volts from the T-stat. And so I'm going to go yellow into the coil, common, which was, one was brown, I think, right? Yellow and, and blue.
Brown and blue.
Sorry, blue
And brown.
and brown. No, yellow. No. One on this side, one on this side. One's blue and one's yellow. Y'all look at these. When you see this on your contactor, power goes in one side and comes out the other. So you've got two wires hooking to it. It gives you two connections. If you don't hook, that'd be two powers on the same side. That won't work. One on this side, one on that side, please.
On contact, is it negative and positive?
Either way, no polarity. It'll work as long as you have 24 common. All right, so that is my picture diagram. Thank you, sir. And when you look at this, like you will later on, I'll pull all the wires off, and hopefully you made a good wiring diagram. You can wire it just back like it was. Because you labeled the colors, right? And you said, hey, this color goes from this one to this place, like a road map. Yes, sir.
Now, on that fan, the wires not going to always be black, yellow, and brown. Sometimes
Not always. And we're going to learn, we can either look at the motor and read, see what it says it is, or we're going to use our meter today to learn how to figure out what one to run, start, and common. A lot of you already know how, but we'll go over it again. So, want to learn to use a schematic. Okay? Because it shows me much clearer how this thing works. Not how to install it, how to replace something, how to rewire it, but how to troubleshoot it. So, schematic diagrams are broken down by voltages. You always start with the highest voltage. So the highest voltage thing I have in here is we're saying 240. And so I'm going to start with 2 hot legs, L1, 240 volts AC, and L2, I guess I should write a 2 instead of a 1. Okay? Do we have any power flowing in? Over here, you'll see, I wrote on here, 240 volts input. So that's to simulate, and that would go to L1 and L2, right? Didn't we leave that blank here?
Yeah.
And so this would be our power if it were going in. All right, so I'm going to give you 5 steps here. I would highly recommend you write them down. Step 1, all line voltage. Now y'all, this is considered line voltage. If it's not line voltage, what kind of voltage is it?
Low.
It's load side, but what other voltages do we have besides line voltage? Line voltage isn't necessarily 120 or 208, 230, 240. It's not control voltage. In our case, control voltage is 24 volts. So everything that's not control voltage is line voltage. So all line voltage, step 1, into the contactor. Isn't that what we did here?
All that goes
Into the contactor. So how do I draw a contactor? Whoop. Isn't that it? Isn't that what that has? A normally open automatic switch? It's an open contactor. That's step 1. Now, notice I have labeled these open contacts to tell you, the reader, what controls the compressor contactor coil controls. Step 2. That's step 1. Step 2. T1 to the motor commons. How many motors do we have? 1 inside the compressor and 1 for the condenser fan motor. Do y'all remember the symbol for a split phase motor? Told y'all that first test of symbols. That's a motor, right? Compressor, condenser fan. So I said from T, if this is L1 right here, right? Isn't that L1? Then across from it is T1. If this is L1, this is T1 across from it. So from T1 to the commons. I don't need wire colors on the schematic. We don't care about that. I'm sorry, I'm right in the room. Well, there's another type of pressure switch you were asking about. That's a high pressure cutout. I didn't have one here to show you. Sorry.
Step 2 is
T1 to the comp. T1 to the comp.
What's the common like?
In this case, they're both black. both those motors. To the common, plural. Yeah, to the common on the compressor, to the common on the fan motor.
Common wires, looking up to the.
Well, it may be that you have a terminal, that's what I'm saying, to the common. If it's a wire, that's cool. Okay, step 3. From T2, not T1, T2 to the runs. If this is L2, across from it is what? T2. That's right.
The first line 1 CC is T.
Contactor. Contact.
L1, T1.
That's right. L1 will be incoming from L1.
And T1.
L2 would be from L2, and then across from it would be the T, right? L's mean line side, T's mean the load side of the contact. Did everybody get that one? All right, 4 from T2 through the capacitor to start. T2 through the capacitor to start. So this is T2, right? What's my symbol for a capacitor? And I got a label. What kind is it? A run. Run capacitor, right? I know it's hard to see back there, but I'm running out of space. I put a capacitor symbol in there, didn't I? Remember? That's a capacitor. And I labeled it a run capacitor. One here going to start. One here going to start. One more step, that's it. And the beauty of it is almost every time we have a single phase motor, it's just like this. Now sometimes we'll have to add a start capacitor and relay to it, but this is with us from here on out if it's BSC motor. So step 5 is all those things listed on the board, those 6 things, what have I not hit? Look at those items. What did I not wire up? Which one had 2 things? Contactor is what? A switch and a load. That's right. So do we know the symbol for a coil? What am I going to label this? Right? Now, does this thing work off a 240? No. If you draw this 240 to it, you're going to blow that contactor. So I'm going to have to either have a transformer, which there was no transformer in there. I've seen a York unit with a transformer, but usually the transformer is always on the inside. So I'm going to say 24 volts AC from T-step. Why? Because this not the same voltage, it breaks. Okay. Who's got their electric meter? You do? You set it on ohms and come on up here and help me out. Let's see if we can.
Was that step 5, 24 volts?
Oh, now?
Was that step 5, 24 volts?
That's right. Wheel that one out in front of the class, please. All right. You don't have alligator clips? You would get them. Okay, so I want to talk about your lab today. Can I make this bigger? Yeah, maybe that'll help. So, this lab, see. A VSC motor or split phase motor, sometimes a single phase motor. Single phase, split phase motor, same thing, just different terminology. A PSC motor, what we use most of the time, is a type of single phase or split phase motor. Because PSC means permanent split capacitor. In other words, it permanently has a run capacitor attached to it. Capacitors, as we saw from this diagram, always are wired up to the start terminal. Now inside this motor, inside this compressor, there is a motor. But just like inside this condenser fan, it's the same type of motor. It's a PSC motor. And inside it, we got two windings, we said, right? We have a winding we call run. We have a winding we call start. We said the run winding was thicker and shorter. The start winding is longer and thinner. Inside the motor there, y'all, inside the motor, we connect the two windings. I can either connect those two or these two, but I think these are close together. So I am going to hook these together. Does that make sense? They are connected by electrical conductor, either brass or copper. And I'm going to make a place for us to get electricity to it. And I'm going to call it common, because it is common to both of them, isn't it? Now, two windings, or two coils, I have a common terminal, and now I have two terminals at the end, right? So at the end of the run winding, this is the run terminal. At the end of the start winding is the start winding. So, if you would, he has a motor up here with three windings, and we have no idea which one is which. Because let's say this is you in the field, and you're like, how do I wire it up, Clay? I know how to wire it up, I do the terminals. And they look like this right now, I think. Is that kind of the triangle we got? One on top and two on bottom? Mm-hmm. All right, he is measuring from the bottom to where? To the top. will?
Yeah.
Alright, measure, keep one of them and move the other. You are on. Okay.
You want one on the top?
No, just across the bottom now. Now, whenever you start owning something, y'all, you always want to touch them together, make sure your own meter works. And his is 0 now. Now, you're going to go from the bottom left, top left. I'm going to get another compressor. Yeah, come on. Hang on.
So that's how we find the back compressor.
That's how like an open, like those over, like overload on it or something.
You don't have no pad.
Alright, back again. Alright, so we got a little different configuration. We got kind of one on the bottom and two on the top now. So we'll take one on the bottom and two on the top. And you're going from where?
Bottom to bottom. Just count like turn 3.2.
So from here to here, he got what?
3.2.
Alright. That's your first read.
From the devil over there to the devil at the top, right there.
From here.
To there. I'm good. 0.6. 0.6.
Remember, this is what's going on inside, but we don't know how they are. That's from here.
Yeah.
Thank you, sir. Okay. So you get 3 readings, right? Somehow inside of this shell, I have a common and 2 coils. What I want you to do is, step 1, determine what the highest reading is. I have 3 readings. What's my highest reading? 3.2. Right? Now, what terminal is not used in that reading? To get this reading, I'll use these 2 terminals, didn't I? And that was the highest. If this had been the highest, then these 2. But to get this one, I didn't use. So the first thing is, when you find the highest one, the terminal not being used is common. That's my first rule. Second rule. What's my second highest reading? 2.4, right? I've already used this one, right? All right. What two were used in this one? The second highest rule gives me which one of these has a higher resistance? The longer skinny one. So the second highest reading gives me start. Now, I don't know which one is start. The second rule only tells me that start may be one of these. But we know the first rule already told me that this is, and so that means this has to be. Now, you can either go whatever's left is run, or you can go the third rule is what's the lowest reading? 0.6. One of these is run, one of them's common, but the first rule told me that this was common. Does that make sense? Now, take a look at your lab that I gave you. Over here, on the other side, there's a bunch of compressors labeled A through, what does this go to, K? If you can't find one, then come to me and say, Clay, we can't find C. Probably means somebody ripped the paper off of it. We'll fix it. Just come tell me. But first of all, y'all see that? A through K? You're going to go to each one of those compressors and you're going to do Terry just did. You're going to own them out. Now, first of all, it says good or bad. Y'all, if one of these windings inside of here, there's a winding, right? We said that was common. And you see why this is the highest, can't you? Your meter had to run through the start winding and through the run winding. It was both windings put together that gave us the 3.2. But if anywhere in here this wire is burnt open, it's going to read what? Oh well. Then it's bad. Another thing is, if this thing anywhere in here, you can touch the copper. See the copper coming out on the refrigerant lines? Either the suction line or the liquid line. If you can touch one of your terminals there and touch any of these, and it reads anything but OL, then it's grounded, it's bad. Okay? The only thing that means it's good is what? MR, measurable resistance. 3.2, that's a measurable resistance. 0.6, that's a measurable resistance. See what I'm saying? But OL or 0, not any good. All right, now, do you see where it says start and run? I want you to give me the resistance on that compressor of the start winding and the run winding. Now look at this. On this example, what would be my start reading? 2.4, right? Because 3.2 is both of them put together. Which one would be my run? All right, so everybody understand we're going to do our lab. And next time we'll do one for just a little fan motor, but we're going to start with the compressors. Did you have a question? Okay. All right, y'all, you got your lab. Please remember to memorize those symbols and those few definitions. That's what will be our test on Wednesday.
All these symbols right
Yes, yes.
You got some handouts out.
I gave